solve them, or you want me to solve them? No? Okay, you solve these two equations, two unknowns, you have the solution to this problem. Okay? This is not exactly the same one in the textbook. In the textbook, there's one additional resistor over here. But the idea is the same. You can do the same thing. Okay, there's another example of control current and voltage sources in the textbook. I can go over that example with you. Or I have about 13 minutes left, and I can talk about something else. Okay, but let me talk about something else using this remaining 30 minutes instead of going through another example of control current and voltage sources, and then using KCL and KVL to set up the equations in this problem for the unknowns. Let me talk about capacitors and inductors. The VI relationship of these capacitors and inductors. We talk about the VI relations of a resistor. That's very simple, just V equals IR. But capacitors are a little bit more complicated. Okay? The current flow in the capacitor is dV dt. Okay? Capacitor measure their charge storing devices. They're made by just having two parallel plates. Okay, the parallel plates can be made in any fashion. They can be flat, they can be wrapped up in a Swiss roll fashion so that they look very tiny. But if you open up a capacitor, you'll find two parallel plates as you unfold a parallel capacitor. So a symbol for a capacitor is just this. Okay, you can apply the voltage to this capacitor. Maybe you can say the bottom one is connected to ground so that this is 0 volt. What happens is that charges will start to accumulate on the terminal connected to a positive voltage. These are positive charges. Okay, current will be flowing into this capacitor. But this capacitor is not connected between the two plates. Eventually the current cannot flow. The current cannot flow. So what happens is that in the initial moment when you connect the voltage source sees no resistance. So easy to go in, right? Nobody is obstructing me. Nobody is preventing me from sending charges into this device. But as time progresses, what you find is that it's harder and harder to send in the charges, because the charges that had been there will say, you guys don't come in, I'm already here. Okay, I'm positively charged, I don't like you. If you come in with a positive charge, go away. Okay, if you come in with a negative charge, that's fine, you're welcome. Okay, but if you're sending a voltage source, like to send positive charges to the capacitor, so that actually would build up charges in the system. And what this equation is saying is that in the initial moment, okay, when the initial moment, there will be no potential drop between these two parallel plates. V is 0 in the very initial moment. But the moment you supply, so if I plot V as a function of t, okay, in the initial moment the voltage drop is 0, but it will rise gradually. Okay, it will rise gradually. Okay, I don't know how it rises, but it will rise. And if it rises, what happens is that this parallel plate will get saturated with charges, and then it cannot rise anymore. So V of t will look something like this. Okay, that eventually it will get saturated. So the current flow is proportional to the rate of change of V. In the beginning, this is positive, and then it goes to 0. So I of t will look something like that. That's what this equation is saying. The equation is saying that in the very beginning, charges can enter the capacitor very well, and there'll be nice current flowing into it. Okay? But as time progresses, there will be charge built up in the capacitor resisting the incoming of positive charges. And that causes the current to diminish and finally coming down to a trickle and going to 0. Okay, and this is described by this equation. This is what this equation means. If you think about it, dV dt will look something like this, right? Okay, and the proportionality constant is C. C is equal to QV. Okay, C is equal to QV. The amount of charges you can put into a capacitor is proportional. I shouldn't say it this way. I should say Q is equal to C over
Q is
C over V. This doesn't sound right.
No.
That is wrong. Okay, that's wrong. C is not QV. C is something else. Okay. QC equal to V. Okay, which means that Q is V over C. The amount of charges you can push into a capacitor is proportional to the voltage you apply. And this is a constant. This constant doesn't change. Okay, so this is how a capacitor behaves.
C is Q over V.
What? Did I get anything wrong?
C is Q over V. Yeah, C is Q over V.
Yeah, C is Q over V, Q is V over C, right? I can also say C is V over Q. I can also say what? Let me see. Did I get this right? Did I get this right? Let me think. Okay. Let me think. Okay. C is Q over V. I think that's what we learned. Okay. So C is CV is equal to Q. Does this sound right?
Yes.
Q is equal to CV. Right. This is what we learned in your freshman class. Physics 212, hopefully. I'm sorry about that. I haven't taught this course for ages. Okay. So C is equal to Q over V, Q is equal to CV, which means that the amount of charges you put into a capacitor is proportional to the applied voltage. Okay? That is what it means. And this is how it should behave due to the physical reason. And let's look at an inductor then. What is an inductor? An inductor is just a spiral of wires that looks like this, and it is represented by this symbol. But actually, when you make it, it doesn't look quite like that. You might make it in this manner. It might look something like this in real life. Okay, if you open up a radio circuit and look at how an inductor looks like, it might look something like that. But this is hard to draw. This is easier to draw. Okay? So you might open up a radio circuit and see some of the coils, like your tuner receiver. In very old days, they were made of inductors that are wound around a ferrite core. Okay, that's how an inductor might look like in real life as well, but we represent it with that symbol. The peculiar thing about an inductor is the fact that when the current goes around in the loop, what does the current do? When the current goes around in the loop, it generates a strong magnetic field. Okay, it generates a very strong magnetic field. And that magnetic field is generated according to Ampere's law. So I would say that the magnetic field is going like this. Okay, with the right hand rule, okay, the magnetic field will look something like that. And the generated magnetic field tries to resist the flow of current. Okay, there is something called a V cross B force that you might have learned in your other freshman physics course. So the current produces a magnetic field. The magnetic field in turn exerts a force on the current that tries to flow, because the currents are trying to move around in the velocity. Okay, actually it tries to resist the current flow. This is known as Lenz's law. So if you have an inductor, and if you try to set in the current through this inductor, it tries to produce a magnetic field. It tries to prevent the flow of current. Okay, and how do you describe this VI relationship? This VI relationship says that the voltage is L VI dt. Okay, which says that in the beginning, okay, if you try to put in a current into the inductor, the current generates a magnetic field, and that would try to make a very strong voltage drop. So if this is large, if the IDT is large, it produces a very large voltage drop across the inductor. Why is that so? Because if the IDT is large, okay, it produces this B field. This B field will generate a counter force that is proportional to its time rate of change. Actually, it also tries to produce a force by Faraday's law. It produces a counter electromotive force by Faraday's law, and that tries to prevent the flow of current. So in the beginning, if you do have a current flowing, okay, you do have a current flowing, the current would actually be very minuscule. Okay, so if you plot the current as a function of time, the current would look like that. And in the beginning, let me draw it like this. I think it should look something like this, so that the IDT will look something like this as well. Okay, V of t will look something like this, in the sense that in the beginning, when you try to push in the current, the rate of change of the current is very large. It gives rise to a voltage drop that's large. Okay, but as time progresses, the rate of change of current is going to be very slow. And this two diagram was just the opposite of these two diagrams, in the sense that after a while, the voltage drop is going to change very little, because the current is going to go through a constant valley, okay, as you try to push the current through, and then the voltage drop will diminish, and eventually the inductor looks like a short circuit. Okay, the inductor looks like a short circuit, and then here the capacitor looks like an open circuit. So as time progresses, the inductor looks like a short circuit, but a capacitor looks like an open circuit, and that's how things should be. Okay? I guess I'll stop here and continue next time.